All right. So I want to come to a method published in 2007 and a bit earlier at the conference, which is called BM3D for block matching (3D). And you see the block matching that we talked about today again finds its place here. I've chosen this method for a couple of reasons. One is it again builds on patches. It also capitalizes, just like non-local means, on the idea of exploiting the self-similarity that most images have. In addition, it introduces a new twist, which these authors call collaborative filtering, which I will show you in a minute. The main reason, however, is that this has been really hard to beat. So the method is not, a model of sheer beauty. It is somewhat engineered. It has a couple of parameters, which, however, the authors adjusted optimally. And it has really taken a few years and huge efforts to get just fractions of a decibel better in denoising performance. So that is quite a feat. And while this method is not exactly simple, the ones that supersede it are more complicated still. So this is, I think it's fair to summarize it as the bane of theory, this method. It works better than anyone can explain and better than any theoretician would like to acknowledge. And I think more work is needed to understand why exactly it does so well. So the pictures shown here are similar to the ones that you've seen in the non-local means paper. Highlighted in red is always a reference patch, and shown in blue are some of the patches that are quite similar to it and that can be used to better estimate the structure of the reference patch. Here is the basic structure of the algorithm, and the new twist is here. Just like in non-local means, patches that are similar to reference patch are found. They are then stacked here into a volume that has one dimension more. So let's say if my original image is 2D, then they are here stacked into something that is 3D. The patches are usually sorted by proximity to the reference patch along this new artificial dimension. And then a 3D denoising algorithm is used, which changes, potentially at least, the looks of each and every one of the patches in this group. And afterwards, the information is projected back to the image domain. And this projecting back is not so trivial because one location in an image may be part of multiple different groups. So this is what I will describe at length, step 1 of the algorithm, and then step 2 repeats the same thing over again, building on the results from the first step, with the minor difference that here in the first step hard thresholding was used, and in the second step Wiener filtering is used. What precisely this is, I will explain once we've talked about Fourier transform and so on next week or the week after. So we will go through step 1 first in words and then in formula. The basic idea is to denoise a patch. We want to first denoise the image, which as before, is this chicken and egg problem, because image denoising is what all of this is about, really. But anyway, so we use a cheap algorithm to first denoise the image by just smoothing in an edge-preserving fashion. Then next you form a group of a denoised patch, where denoised is, according to the previous step. With similar denoised patches. So this is my reference patch. And then I append in order of decreasing or in order of increasing dissimilarity the most similar patches that I found. So I'm not using all patches from the entire image, but some up to some upper limit. I forget what number is being used. It helps, yeah. So you can omit step 0, but they show empirically that it's better if you do it. And actually, there was a paper written in 2011, I think, by Lebrun in Image Processing Online. Who wanted to provide a reference implementation and clean up notation a little. And he was also hoping to find better settings for all the parameters, and in that failed, showing that, and really there are many parameters in this method, but the authors had really gone to great length to find optimum settings for all of these. So it's, in that sense, highly engineered. Okay, so if we talk about 2D images, then each of these patches is 2D, and we have this extra dimension, so that overall we get out something which is 3D, where the third dimension is special. So in most cases, you would expect to have little variation across this artificial new third dimension. And this works also if your original image is 3D, then this new image is going to be 4D, and so on. So in general, let's call it a D+1 dimensional group. So this is a group, and that's a technical term to remember in the context of this hour. When I say group, I always mean this stacked collection of patches or blocks. So now comes the first interesting thing, namely to denoise this D+1 dimensional group. I will say in a bit more detail how, but really the technicalities behind this we will only understand in a week or two once we've talked about the wavelet transform. Here's the rationale for working or for operating on this D+1 dimensional group. The idea is to exploit the intra-patch correlation resulting from the smoothness of natural images. Note my funny layout, yeah, there will be more words. And this is something that conventional smoothing or denoising methods do. But at the same time, you want to exploit the inter-patch correlation, which results from the self-similarity of natural images. And the idea is to now do this jointly. I didn't want to erase. So there's the rationale of the method. Then, after you've done this to all these groups, and these groups typically comprise overlapping patches, so the same patch can be a member of multiple groups, you somehow need to bring those results back to the image plane, which the authors call aggregation. You're going to see this is an index war. And once you've done all of this, this was just step one, then you repeat this in step two using a different, namely a Wiener denoising strategy. And I promise to explain what Wiener is in a week or two. Okay, if you do that, it's the kind of result that you get. So on the left, a noisy image of someone wearing striped pants at a standard deviation of, so there was additive white Gaussian noise with a standard deviation of 100, which is quite severe. And on the right hand, the reconstruction, which I would say is quite remarkable. So it has recognized, or hallucinated if you want, the texture in the pants even where we hardly see it any longer. And it does not hallucinate too much structure elsewhere. So quite a fascinating result, which is also borne out by the numbers. You can now collect these peak signal to noise ratio numbers averaging over many images and so on, and you then find that the method performs exceptionally well. Okay, in formula. Now brace yourself for indices. I'm using the slightly simplified notation from the paper, so there are some more indices in the paper. It's convenient, huh? You can always blame the authors, but this is why I gave the reference. So if you want to read it up, you can follow this. And as I said, Lebrun, he has offered an alternative notation. So to form a group first, we need to find a set of coordinates or of patches or in the paper they talk about blocks that are similar to the current reference patch. Which is called R, capital R. Sorry, excuse me, the reference patch is not called R, but it is called ZXR. So again, R is for reference. X, this is a small x, is for location. And capital Z means it's a patch of numbers or a patch of pixels, not just a single pixel that we're looking at. Okay. But we want to find a set, and this set is called S for set X R. So it's S subscript X, which is a subscript capital R, which is the set of all coordinates in our domain, such that the distance between the reference patch and the other patch that we're considering is smaller than some threshold. So tau is a threshold, ZXR is the reference patch, and ZX is the patch at location X. Now we need this dissimilarity. And the dissimilarity is found based on these denoised patches. So now I'm using operator notation. So I'm first transforming my, so small tau was this was a small tau, that was a threshold. And here this is a capital script T for transformation. So my patch, my reference patch, is first transformed with a 2D operator, typically a wavelet transform, into another domain. In this other domain, a hard thresholding is applied, and I can then inverse transform to get back my denoised image. So this all in all would be my denoised patch. Let me call this, Z hat XR or something. This is denoised patch, and as regards this 2D transformation and this hard thresholding operator, I just ask you for patience until in a week or two when I will have explained them in detail. So this is a hard thresholding operator. In essence, what is happening is that you transform the image into a different representation, and you make the assumption that in this different representation, the small coefficients are only needed to explain the noise, and you delete or you omit these small coefficients using this hard thresholding operator, and you then transform back. So now we do the same for the patch under investigation ZX. So these operators, the rightmost operators are applied first. So I first transform this thing in 2 dimensions. Then the result is submitted to this hard thresholding operator, and then, comes the inverse transform. And then I'm taking the squared L2 norm of this. So in other words, this is the squared Euclidean distance between the denoised patches. Now there's a small trick here, namely, if I want to compute this squared Euclidean distance, I can also do it in the transform domain. So I don't need to really transform back. This is thanks to Parseval's theorem, or I think it's called Rayleigh's theorem in other disciplines, which I will also show and prove in a week or two. Okay, so we have the square Euclidean distance between denoised patches, and we have the set capital S of patches that look, according to this distance, not too different from our reference patch. XR is just a location. And I have not talked about the groups yet. The groups are coming in a moment. Yeah, so ZXR, this thing here, is the patch around the reference location XR. This is 2D. Oh, it's a transform from 2D to another 2D representation. So you think of Fourier transform, except it's not Fourier, but it's a wavelet transform that's being used. So it's not a projection. It stays in the same dimensionality, but it is transformed to a different space where denoising is easier than in the original space. So essentially what's happening is that it's an edge-preserving denoising, which, however, is not exploiting self-similarity or anything. This is just a prior assumption that natural images are smooth. Full stop. Yeah, because if I didn't take the threshold, if I just, this transform is lossless. So if I transform to this other space and transform back, nothing whatsoever has happened. So it is this thresholding operator that implements the actual smoothing. Yeah, something like that. Something like cutting off the high frequencies, exactly. Except it's, similar. The detail it differs, but that is the basic notion. Yeah. Okay. And then in the second stage, instead of the hard thresholding operator, we would have the Wiener filtering. But let's concentrate on the first stage. Okay, and now comes the D plus one dimensional stuff. So this is the block, or sorry, the group denoising, not block. This is the group denoising. Which these authors call collaborative filtering. So y hat SXR is the D plus one dimensional array holding the denoised group. And this is obtained as follows. First we have Z of SXR. This is what I meant by index war. So this is now my noisy group. This is the collection of patches which are indexed by the set S, which collects all the patches, or which enumerates all the patches that are not too different from the patch located at XR. Okay? But in words, this is just the noisy D plus one dimensional group. And now this group is being denoised in 3D as follows. We have this transformation to a different three-dimensional representation. Again, a wavelet transformation. We then have the hard thresholding operator, and this time we do need the inverse transform. So in essence, what these guys here taken together do is they denoise in d+1 dimensions. So this is a d+1 dimensional denoising. And we need a little more notation. This denoised group is a collection of all the patches in that group. And these patches are, after the denoising operation, also called y hat. Now we have a superscript xr and the subscript xm, where xm is in this set. So these are the group members after denoising. And to be more specific, this is the group member located at xm, but it's not to say where it comes from. I also need to say which group it has been a member of, because this 3D operation, it perturbs all group members in a specific way. So the way in which a patch is changed depends on what other members are in the same group. This is why I need this additional index here. So it's a group member located at xm and denoised by other patches that were similar to that around xr. So to be precise here, zxr. All right, so in other words, the thing here at the top, this is the 3D group. And what this equation says, it tells us what the individual members of the group are called. So this here references the individual members of the group, whereas this thing here references the 3D block as a whole. And this extra notation was needed to discuss the aggregation step. So let's pause for a moment again just to see where we are. We have, I go back a little, okay? We have a reference location XR, and then we were looking for all those other patches here indexed by ZX who have a distance less than tau from my reference patch. And this set was called S. The distances between patches themselves were computed not between the original noisy patches, but between a preliminary denoised version thereof. This is what this equation says here. If we omitted the preliminary denoising, then we would simply leave out this part and would just look at the squared Euclidean distance between the reference patch and the other patch of interest. Then things were stacked into a group. So all the patches that were in this set of patches that was not too dissimilar from the one located at XR, all of these were grouped together and were then denoised in 3D by the action of this operator. So there was some kind of wavelet transform, then hard thresholding and manipulation of these wavelet coefficients here by this hard thresholding operator, and then the inverse transform. So the result of this is a collaboratively filtered group. This is why we have why we no longer call it Z, because Z is the original noisy image, but this is why it's now called Y for the denoised image. However, one patch in the original image could have been a member of many different groups. So let's say this patch here, which I'm painting in red, it is member of the reference group that you see here, but it could also have been a member of the reference group centered somewhere else on the nose. And when we group these patches here, we get a new estimate for this patch because we filter in 3D. But if it's a member of a different group, then we get a different estimate for that patch. And now we want to reconcile all these different estimates, which we do in the aggregation step. Let me try and say in words. Each pixel in my noisy image has probably been a member of several different groups. And by this collaborative filtering, the patch around this pixel was modified in different ways in each of these groups. You could also say that it has learned, if you want to use that big word, you could say that it has learned something different in each group. And now we want to bring all of these estimates together. So now we want to reconcile all these estimates. And for this reconciliation, we weigh, or by the inverse amount of noise that we have in that group. So the idea is that noisy groups get smaller weight, which makes sense. And in the end, we again need to normalize or make sure that the weights sum to 1. Okay, that was in words. Now here's the equation. This is my estimate at location X. So this is the estimated intensity at pixel X after the end of stage 1 of this algorithm, stage 2 being the one with the Wiener filtering. So we sum over all possible reference locations in the domain, and we sum over all the pixels that are in a patch that is not too dissimilar from that around my reference location. And we average the pixel values found in those different patches. And importantly, we weigh with the inverse noise level of that group. All right, that was the numerator. And then we have to normalize. So we have the indicator function that checks if x is in the patch around xm. Multiply with the weight. So the effect of this normalization is just to make sure that the weights sum up to 1. Okay, I still need to define this WXR. This is the inverse noise estimate of group R, and this is found from the coefficients of the D+1 dimensional transform. I'm not giving the formula here. The effect of this is that we give larger weight to not noisy or to smooth groups, smooth in D+1 dimensions. Okay, now I've had to sit and stare at this formula for a while, but I hope I expressed it clearly in words. Each pixel for which we want to make a prediction, each pixel x for which we want to make a prediction can be in a patch or can be in patches that are part of different groups. Each patch in its own group is somehow tweaked by this 3D or this D+1 dimensional denoising. And now we want to get back all this information and put it down at the location X. And this is done with the help of these weights, where groups that are very, groups that disagree amongst themselves. So if all the patches in a group are pretty dissimilar, then the group as a whole will look noisy in the sense that it will have many large coefficients in a wavelet transform, and then it gets low weight in this expansion here. So in a way, this aggregation is a technical detail. The really, really important idea in this entire paper is this collaborative filtering. So to combine these patches into groups and then do a denoising both within a group, both along the original axis that span the image and along the extra new artificial axis that results from stacking all these patches into a group. This algorithm has been very hard to beat, and for good reasons, as I will explain in a moment. But before I do, would be a good time to ask questions about this. You can? Yes. So the question was, can you learn from other images than the one under current study? And that is indeed one of the only 2 papers that I'm aware of that can lead to somewhat better performance. The strategy that you describe in words has been put into math in this paper here. And these authors use not a data independent 3D transform to denoise the group, but instead they learn basis functions from a large set of unnoisy, of perfect natural images, and then use a sparse coding rather than a wavelet transform. So yes, that works, but you have to be aware whenever you do such things, and especially in a medical domain, that you are performing a nonlinear operation here already by means of this hard thresholding, and this means that you can hallucinate things. You can introduce things in the image which are not really there at all. And especially for medical studies or for having a procedure approved by these medical boards, that is a big obstacle, and rightly so. So I don't have the pictures here, but one nice example is from super resolution, where using nonlinear methods, you get much, much better results than using linear methods. Super resolution means you get a low resolution image and you produce a high resolution image out of it. So in most cases, these nonlinear methods work much better, but sometimes they really hallucinate things which are simply not there in the original image because it was there in one of the learned images. So yes, it's possible, but there's this caveat. Good question. More questions? Y hat in this formula is just a single patch out of the group. Yeah, Y hat is a patch, and it's one that has already been denoised. Yeah, so capital Y hat, so this thing is a patch, but we're reading it out at location X, so this is a single pixel. Yeah, the indexing here is the trick. Yeah. It's very subtle. The idea is not that difficult, but it's really hard to write it down simply. So we are looking at all the groups XR which have the current pixel in it. So Y hat is 0 padded. Something I didn't know. So Y hat is 0 padded. Oh, sorry. I'm still in the pointing out stuff mode. So Y hat as a whole here has been 0 padded, which means that let's say this is the location of my pixel X, and the patch that I am pointing out here would be, if I take the noisy version, would be Z, X, M, X, R, where R means R is essentially the index for the group, and XM is an index for the group member. And then X in itself gives the position within a group member. Okay, I think this is war by committee. You should look look at the formula a bit more by yourself. Okay, so BM3D has been very hard to beat. There are minor improvements possible, one of which you have already suggested. So these people here use sparse coding, which has been learned on a large data set of noise-free natural images instead of the wavelet transform. Yes, I have it in the... So if everything goes by schedule, yes. But there are other, if we run out of time, then this would be one of the things that I may omit. There's a paper here which uses this one here, uses BM3D as a subroutine. And well, it does a little more than that. So it allows you in particular to deal well with structured noise, which is a wholly different, which is a different story from the white noise that we've been looking at so far. But if you use BM3 as a subroutine, you're already starting from a pretty good level. And I mentioned that BM3D has been the bane of much theoretical work, and I want to point out 2 papers here. So CVPR is one of the 3 or 4 best conferences in computer vision, or 2 or 3 best conferences in computer vision, and this is last year. So this is really current work that I'm showing you here. These people used a neural network on 362 million training samples, spending 1 month of GPU time to train the neural network. And if they train their neural network on sigma equals 25 standard deviation, then out of 500 images, they are better than BM3D on 300 images. And it's just the learning that is slow. The training is slow, so predictions are actually very fast. However, if you then look at other standard deviations, so at images with more or less noise, you see 25 is the regime the neural network was optimized for. And there, if we zoom in really far, then the red line, which is the neural network, or sorry, the brown line, which is the neural network, is a little bit above the blue line, which is for BM3D, just enough to be better not on 250 out of 500, but to be better on 300 out of 500. But if you look at the absolute scale here, you see that we're really talking about fractions of a decibel here, at which the neural network can be better at sigma equals 25. And then at other sigmas, the neural network is a lot worse because it's, it's just been trained to do that one thing. You can also have a neural network. This is the green line trained on different noise levels. This is the green line, which is not as catastrophically bad anywhere, but it's also not quite as good as BM3D at sigma equals 25, and especially not at lower noise levels. Yeah? So you see there's a bit of discrepancy here. Now, these are very smart people, and they've trained a pretty good algorithm on a very fast computer. All this goes to show is simply that BM3D is really very, very good. So to put this into perspective. Okay, and the authors faithfully and frankly discuss all of this. Then I want to point out another paper from DHM 2012. Stefan Roth is one of the inventors of the field of expert, which is a very important model. It is a higher order Markov random field where the potentials are trained rather than pre-specified. So in a way, the field of experts model is a successor of the frame model by Zhu and colleagues that I talked about. But in this paper by Zhu, they pre-specified the filter bank, whereas field of experts can learn the optimum parameters. And well, on a single image, it is possible to become a tiny little bit better than BM3D, but I think this does not hold for larger data sets, if I remember the oral talk correctly. Also, this is theoretically a very nice piece of work, and it won the DHM prize, this paper, but it doesn't really manage to do better than BM3D. I wanted to point out a paper, if you're really into this topic, this has come out in January, a paper by Milan Far, and it's in IEEE Signal Processing magazine, which is why it has such, a much nicer layout than you find in ordinary papers. And he offers a different perspective of, let's say, a unifying perspective of a number of denoising algorithms, trying to explain why they work well. So, I repeat the question by Boaz Nadler. Should you go for a career in image denoising? And they have a paper out in 2011, Boaz Nadler and Anat Levin, where they say that at least for small patch sizes, we are pretty much at the limit. So they use a non-parametric model and offer an upper and a lower bound. So the red line is an upper bound and the blue line is a lower bound of the achievable performance as a function of the patch window size that you are going to look at. And you see that BM3D, the green dots, is really, really close to this upper limit, which probably also explains why these other algorithms, if they manage to be better at all, it's really only by fractions of a decibel. Having said that, this paper here has two restrictions. One is it looks really only at relatively small patch sizes, and the theory doesn't work as well for larger patch sizes. So you may, in principle, still be, if I go to a patch size of 50, in principle, it's possible to, or at least no one has found a reason yet why it's not possible to get a greater performance there for very large patch sizes. The other limitation is that they were looking at mean squared error as a metric in their study, which is the only thing that is tractable mathematically. But ultimately, mean squared error does not mimic human perception well. So if you could construct an algorithm that really understands that this is a squirrel sitting on a rock, then perhaps this algorithm, could do perceptually even better. But at least for small patch sizes, it seems we have reached the limits of what is possible today. So there's another interesting piece of work that I don't have time to talk about. If you have really caught fire, then I encourage you to look at this paper by Daniel Zoran and Yair Weiss from last year. I will not explain what's in it. I will close with two things. On the one hand, a website that Torben pointed out to me. So IPOL is Image Processing Online. It's a nice journal that tries to foster reproducible science, offering code and so on. And here you have an online demo where you can pick one of the pictures and then the noise level. I've taken this picture and noise level of 40. So this is what the noisy image looks like. This is what the denoised image with BM3D looks like. This is the difference between original and denoised. But remember that the noisy image looked like that. So the patches in the floor, which we lose, the tiles on the ground, I think they're really hard to see in the noisy version. And there's the difference. And the difference tells you where this assumption of always being able to find similar patches breaks down. So in particular, in the original image, we have a lot of distinct structure here at the silhouette of these trees. So we have lots of different angles here and so on. And these are areas that come out strongly here in this difference image. So this is one parting observation, and the other is, again, that we have today looked mostly at methods that did not require training, and that were in that sense prior free, so purely data driven. So super short summary of the last two methods I discussed are that non-local means and BM3D do not need a training set besides the image to be denoised. In that sense, they are purely data-driven and prior free. This paper that I didn't have time to talk about by Zoran and Weiss is all about bringing the priors back. So, okay, so today we've talked about what you can do with patches and that it's important to let the data speak. And next week we will give a somewhat more theoretical flavor. Next week I will talk about unitary transforms, in particular the Fourier transform, and how you can understand signals in this reciprocal space, how you can design filters in these reciprocal spaces. I will try and explain why, out of all conceivable transforms, the Fourier transform plays such a special role. And generally speaking, next week I will summarize a very well understood piece of math, so much better than understood than what we talked about today, that has been at the heart of image analysis for 30 or 40 years until machine learning came along. So I think it should be fun next time. Thanks very much.